Hello, welcome to another Stat 510 video. In this video, we're going to talk about variance and covariance, and really we're just continuing talking about expectations because, as we'll see, a variance is really just a specific expectation if we think about it in a certain way. Okay, so that is, we want to define the variance of a random variable x. This random variable we're going to assume has an expected value that we can call mu. So we use sigma squared as symbolic notation for the variance, and it is essentially the expected value of x minus mu squared. And related to the rule of the lazy statistician that we saw before, we can then write out the specific definition for a discrete or a continuous random variable. So in the discrete case, it's something like this. So what did I say? X minus mu squared times f of x. So this is for x discrete, I think I said. And then if we integrate instead, in the continuous case, that is the variance. So again, we have a bunch of different notations for this. Sometimes we use sigma squared. Sometimes we use sigma squared sub x. Sometimes we'll use the v instead, like the e for expectation to mean variance. But all those things mean the same thing, which is the expected value of x minus mu squared. That is just the definition of the variance. And then you apply the rule of lazy statistician to get an actual expression that you can calculate. Okay. Yeah, so I think it's really helpful to think, oh, it's just, it's a very specific expectation. It's a very specific function of a random variable that we're interested in. Okay. And then related to the variance, we often quickly define the standard deviation, which is just the square root of the variance. So often we use sigma, not squared, so just sigma, notationally for that. Oftentimes in practice, like when you're doing data analysis, talking about standard deviations instead of variances is really helpful because the units are no longer squared. They're the original units of the variable you're looking at. But I would note in theory, when you're working with standard deviations, it's often helpful to keep everything in terms of variances until you need to get to a standard deviation. So if you're given standard deviations or something, and then you need to calculate a new standard deviation, go through the variance. I don't know if we'll see an example where I do something like that, but something to keep in mind. I think it's always easier to work with variances. Okay. So 3 properties of the variance here. So this first one is a really helpful expression for actually calculating variances, which I think we'll utilize on the next slide. The next one tells you, if you take this affine transformation, what happens to the new variance. So the way to think about this is if you have a random variable and you add a constant to it, that just kind of like shifts the distribution over, if that makes sense, or the other way. So that doesn't affect the variance. But if I multiply, so if I have like a discrete distribution with potential values 1, 2, and 3, and then I multiply that distribution by 4, well, now they're more spread out, so there's more variance. So that's the intuition between squaring the coefficient, but then dropping the plus b term there. Okay. And then the last one, which I need to write down now. So we have x1 through xn independent, as well as some constants. So if we look at this quantity here, so ai, xi. So now if I take the variance of this, that becomes sort of similar to linearity of expectation, but we have to square the constants. So it's a similar looking equation here. So we have ai squared, variance of xi. Okay. yeah, let's use these real quick. So I would say that the definition is obviously important, but I would say a lot of times when you're dealing with variances, these are the things you're going to be using more so. Okay, so another example. So, yeah, example. Okay, so let's say x is a binomial random variable. And for a second, we'll sort of pretend for a moment like all we know about the binomial is its probability mass function. So what I did here is wrote out the variance by definition. And then to get a nice looking answer here, we'd have to do a bunch of algebra. But I don't want to do that. Please don't make me do that. So again, I could do the thing I always do where I reach on the shelf, I get out the book, I show you the table, I say, hey, just look it up. And that will be totally fine here. It's going to be n times p times 1 minus p. Like, you probably already know that. But I want to show you how we would use some of these rules to go through that Bernoulli trick we did last time with the expectation. So we're going to redefine x to be the sum of a bunch of independent Bernoullis. I don't think I said that, so I should say Bernoulli. Okay, so if that's the case, we already know the expected value of each xi is p. We saw that last time. So now what I'm going to do is get the expected value of xi squared. Okay, so again, xi can only take two possible values. So it can take 0, so 0 squared times 1 minus p plus 1 squared times p. That's p. Okay, pretty easy. So now I can get the variance of each xi. Something like this. So using the first property here, this would be the expected value of xi squared minus the expected value squared. This whole thing squared. And that is p minus p squared, which I think looks better as p times 1 minus p. Okay, great. Okay, so now we can use the last property here to get the variance of x finally. Okay, so plugging in our redefinition of x. Nope. This would be sum of the xi. Okay, so there's no, well, you can either say there's no constants here or they're all 1, so when we square them it doesn't matter. But basically we can bring the variance inside of the bring the variance inside the summation now. So we get the sum of the variance of each xi. Okay, and so we can sub in what we know. So p times 1 minus p. So adding that up n times, what do you get? You get n times p times 1 minus p, like I said. And we can look that up and verify it, but it's right. Okay, so yeah, so three different ways to get this variance. Look it up, do a bunch of algebra after the definition, or be clever and use some of these properties here. Okay, what's next? Okay, so this theorem is going to have 3 subparts, but the setup is what I like to I call this the classic setup. So, you're taking a math stat class. This setup, we work underneath the setup all the time. So we have x1 through xn that are IID random variables. We don't know the exact distribution of each of these random variables, but they all have the same mean, mu, and they all have the same variance, sigma squared. Okay, so 3 things. First is that the expected value of x bar, I'll give it a sub n, is equal to mu. And here we should probably define x bar sub n is equal to 1 over n sum of the xi. This is the sample mean. I want to pause and be careful for a moment. So this is the sample mean, but it is a random variable because each of the xi is a random variable. So we're not actually acquiring a sample and then calculating this quantity. We're talking about, well, these are random variables that we could potentially obtain a sample and then calculate this thing on, but it's just a random variable for now. So this is still probability land. We're not doing data analysis here. Okay. So 2, no, I want blue. 2, the variance of the sample mean is equal to sigma squared over n. And then lastly, the expected value of s sub n squared is equal to sigma squared, that is the individual variances, where, and you probably guessed this already, s sub n squared is equal to 1 over n minus 1, sum of the xi minus x bar n squared I equals 1 to n. And what do we call this? Well, this is the sample variance. I'm realizing my face is in the way. Well, let's temporarily put me here. Okay, so a couple quick things here. This is a graduate level course, so it's my assumption that everyone knew this already. But I'm going to say this because I found that in the lower division courses, these are things that folks would write down on a note sheet that they might be able to use for an exam. And then for some reason, they don't ever have recall of these things. Now, what I'm going to say is that this stuff right here, this one slide of notes comes up so often. I think that anyone that calls themselves a statistician should have instant recall of this information. I'm looking at it now to make sure I didn't put any typos on this particular slide. Oh, that'd be embarrassing. But these are things you just got to know instantly. I think some of this stuff, the very basics like this, it's, I know it looks like a lot of notation and a lot of, ink on a page, in notation and symbols and jargon, but really this is like one of the core theorems in mathematical statistics. So I think if you don't already, go ahead and memorize this. Okay. Enough rambling about that. Okay, so we've kind of started talking now about multiple random variables at the same time, but we've mostly been dealing with them when they're independent, save for a couple cases. So now we want to say, okay, let's start to talk about how variables vary together. If only we had a good term for that. Okay, so we're going to have two random variables here, x and y. X has mean mu sub x, variance sigma square sub x, similar for y. Okay, so first we can define the covariance of x and y. So that is going to be the expected value of x minus mu sub x times y minus mu sub y. Okay, and then similarly, correlation is defined. So here we have a few different ways of notating that. Often we use rho, but by definition, what it is, it's the covariance of x and y divided by the square root of sigma squared x, sigma squared y. Okay, so correlation is something that I think most folks are exposed to first from a data analysis side. So you'll plot a scatter plot of a couple of things and calculate the correlation, that kind of stuff. But this is not that. This is what that is trying to estimate. Again, this is still a probability concept. So this tells you how closely related linearly the two distributions are. Okay, so that's something to keep in mind there. Some properties of the covariance and correlation. So covariance, sort of similar to variance, it has this formula here that is often more useful for actually calculating it. So that is the expected value of xy minus the expected value of x times the expected value of y. And if you think back to some properties about independence and expectation, you might think of something there. I'll reveal the answer to that in 2 seconds. So correlation, again, everyone probably knows, it goes between -1 and 1. So -1 being smallest it can be, 1 being the highest it can be, but both -1 and 1 being perfect correlation. It's just the direction of it. And then lastly, third thing here. So if x and y are independent random variables, then the covariance of x and y is 0. And so is the correlation. Just because, if you plug in 0 here, it's going to make it 0. Okay, but the thing to be very aware of with that is that the reverse is not necessarily true. Oh boy, I can't write. Not true in, oh my gosh, in general. Okay, so it can be true, but it's not always true. I leave it as an exercise to the reader or viewer to come up with an example where we have a covariance of 0 but dependent random variables. There might be an example in the book, but think about it first before you look it up. It's interesting. Okay, couple more properties of the variance. Variance of x plus y is variance of x plus variance of y plus 2 times the covariance of x plus y. But more generally, so remember, we already talked about this in the independence case, but if we have x1 through xn that are not independent, this is the formula for the variance of the sum of ai, xi. And so here's the part that it was when they were independent, but then when they are dependent, we have to add in the covariance terms. Okay, and so to think about this, it's helpful to think about the variance covariance matrix. So first, I want to define this random vector x that contains elements x1 through xk. So then the mean vector is the expected value of x1, expected value of x2, expected value of x3, all the way through the expected value of xk. So the variance covariance matrix, sometimes denoted sigma, sometimes just the variance of x. So it's this matrix where on the diagonals, those are the variance elements, right? And so that corresponds to here, right? And then so on the off diagonals, you have the covariance terms. And that's what we're looking at here. And then it turns out that the, it's symmetric across that diagonal there. So that's where this 2 comes from. Because, for example, this element here is exactly this element here. Because covariance of xy is equal to the covariance of yx. Okay. I don't know if we wrote that down somewhere, but maybe exercise if you were prove that the covariance of x comma y is equal to the covariance of y comma x. Convince yourself of that. Okay, so yeah, that's it for variances for now. As always, if you made it to the end of the video, good job, and I will see you in the next one.